Chapter 4 discusses probability. Probabilities can range between 0 and 1. They're going to be in percentage form. So the probability is interpreted as the numerical measure of a likelihood that an event will occur. So it's a chance that something will occur. A probability of 0, the event is like totally not going to happen. A probability closer to 1, a 100%, it's definite. 99%, really, really close to definite. 80%, good chance it's going to happen, that kind of thing. Probabilities can be calculated through a series of different experiments, and these experiments have associated outcomes. So a coin toss experiment could have an outcome of heads or tails, since, assuming that coin is not weighted, that would be a 50-50% probability for each of those. But there's probabilities that, we may not necessarily know and might have to be calculated through relative frequency analysis. That might be the number of defective or non-defective parts in an inspection. Whether or not someone purchases a product based on a sales call, those types of things. So those are the probabilities that we don't automatically know. Same as playing, a football game, win, lose, or tie. Probabilities that are sort of known, there's a 1/6 probability of rolling any, a 1 through 6 on a die, assuming, again, the die is not weighted. So there's a 1/6 chance of any of those. The probability of getting certain cards to come up, those are also known, those types of things. Assigning probabilities, the classical method of assigning probabilities based on the assumed equally likelihood of each outcome. So that would be something that you would see for things that are clearly known, like the die rolling, like the coin flipping, like the cards, those kinds of things. The relative probability method is going to be something that you would see, a relative frequency method is going to be something that you would, see in a more application type thing. So how often does a sales call result in actually making a sale? How often is the part actually defective? How often are you actually going to be profitable? Those kinds of things. So here, the classic example, again, as I was saying before, the die rolling experiment has a sample space of 1 through 6. So sample space is all the potential outcomes that could occur for each in each event that we run this experiment. So each sample point has a 1/6 chance of occurring because they're all equally likely. So the probability of any of the events occurring within that sample space is 1/n, where n are the number of elements within the sample space. And again, that occurs when each potential outcome is assumed to be equally likely. Relative frequency example would be, let's say in this example, Lucas Tool Rental would like to assign probabilities for the number of car polishers it rents each day. Official records show the following frequencies of daily rentals over the last 40 days. So they have rented between 0 and 4 polishers. So their sample space is 0 to 4. And this is the number of days on which each was rented. So they rented 0 polishers on 4 days, 1 polisher on 6 days, 2 polishers on 18 days, 3 polishers on 10 days. You get the idea. So the probability of each is then calculated. So we're looking at a total of 40 days. On 4 out of those 40 days, they rented 0 polishers. So the probability of renting 0 polishers on any given day is then calculated as 4/40, or 10%. They went through and calculated all of these individual event probabilities based on past histories. And as we can see, the probabilities have to add up to 100%. So the sample space is from 0 to 4, and all of the probabilities must add up to 100%. So all the probabilities within that sample space must add up to 100%. So there's a 10% chance of renting 0 polishers, a 25% chance of renting 3 polishers, and so on and so forth. counting rules for experiments. Let's say that you have a multi-step experiment. In a multi-step, or if an experiment consists of a sequence of k steps in which n1 possibilities results from the first step, n2 results from the second step, and so on and so forth, then the total number of experimental outcomes is given by the multiple of each of the additional steps. So there are n1 possible results in the first step, n2 possible results in the second step. So it's each of the steps gets denoted with a number going up till k, and then we multiply together all of the potential outcomes that could occur there. So we can go on and say, well, what if a combination must occur? So combinations to count the number of experimental outcomes, or n objects with small n, can be selected from a larger set of big N objects. How does this work? So we have our combination formula, which you're probably familiar with from high school. So it's a combination of little n from big N, so big N on the top, little n on the bottom. Now we're going to be using the mathematical exclamation, and I'll go through and show you on a separate video with using a calculator emulator how that would work. But remember, the exclamation is take all of the numbers and multiply them together. So if this was, say, big N is 9, then it would be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what that N exclamation point would mean. So we have little n there. Little n must by definition be less than big N. So let's say this were a 3. That 3 exclamation would be 3 times 2 times 1, and then the difference between those two there. Permutation, this would be the formula where order is in fact important, and we see the equations for there as well. I will go through and show you examples in a separate slide. So now moving on to the example that we're going to be using for the rest of the presentation pretty much. We have Bradley, and it's a company that has invested in 2 stocks, M-Markley Oil and Collins Mining. Bradley's determined that the possible outcomes for each of the next 3 months are as follows. They can either gain or lose in thousands of dollars. So M-Markley Oil can either gain 10,000, gain 5,000, break even, or lose 20,000. Collins Mining can either gain 8,000 or lose 2,000. So for M-Markley Oil, N1 has M-Markley Oil is event 1. There are 4 possible outcomes there: a gain of 10, a gain of 5, break even, or a loss of 20. Collins Mining has 2 potential outcomes: a gain of 8 or a loss of 2. So the total number of experimental outcomes is the number of events times the number of outcomes of each event. So 4 times 2 is going to be 8. So there's 8 potential experimental outcomes that we will see here. That was as we saw in the counting rules for multi-step experiments. So let's see what those 8 potential outcomes would look like. That can be demonstrated, not really sure what came up there. That can be demonstrated in a tree diagram. So we have our 2 potential stages, M-Markley Oil and Collins Mining. Now we're calling them 2 potential stages when in reality they're happening at the same time in each month, but we're still looking at the, we're going to call them stages because they are occurring independent of one another. So M-Markley Oil can gain 10, gain 5, break even, or lose 20. M-Markley Oil can gain 8 or lose 2. So these are, in each month, we can have all of these different potential outcomes. M-Markley Oil could gain 10 at the same time that Collins Mining's gain 10, or gains 8. So that would be an outcome of 10, 8, which would be a total gain of 8,000. following that first branch again, let's say Markley Oil gains 10, but Collins Mining loses 2, so that event outcome would be 10 comma negative 2, it would still result in an overall gain of $8,000. So you can work through this decision tree and we would come up with these range of potential experimental outcomes. Now, probabilities can be assigned to these. Let's say we used our relative frequency information from past outcomes and we've assigned probabilities based on that. So we know the probability of an $18,000 gain from this total investment is 20%. We know the probability of an $8,000 gain from this investment is 8%, and so on and so forth. So I'm not showing you in this example how these probabilities are calculated. We're just going to take them as given and use those probabilities to do some analysis. So event probability. An event is a collection of potential sample points within that sample space. The probability of an event is equal to the sum of the probabilities of the sample points of that event. Okay, now that doesn't sound like it makes a whole lot of sense, but let's think relative to our example here. Let's say our event is that Markley Oil was profitable, and we're going to call that event M. So if Markley Oil makes a profit, we're going to call that M. If Collins Mining makes a profit, we're going to call that C. So the probability that Markley Oil would be profitable would be the sum of the probabilities of each of the occurrences where Markley Oil is profitable, irrespective of what happens with Collins Mining. So if we see this first section here in event M, you see that we have a positive number in each of the first sets here. So a 10, 10, 5, 5. So those are all of the potential positive outcomes for Markley Oil here. So the probability of those occurrences for those sets, those pairs where Markley is positive would be 20% plus 8% plus 16% plus 26%. So the probability that Markley Oil is profitable is the sum of all of the probabilities of the sample points that satisfy that event. So that has a probability of 70% that Markley Oil was going to be profitable. Now, what is the probability that Collins Mining is profitable? That would be any events or occurrences where we have a positive number in that second term that we see here, irrespective of whether or not there is a positive event for Markley Oil. So here we have 10, 8, 8, 5, 8, 0, 8, and then negative 28. So in this last occurrence within that event, last sample space within that event, you see that Markley Oil is in fact not profitable, but Collins Mining is. So we're still going to include that in there. And we add up all of those probabilities and we come up with a 48% chance that Collins Mining will be profitable. So we can look at events and understand them, break them down a little into some notational references. So two events are complements if the event consisting of all of A sample points that are not in A. So event A and the complement of event A. So an event A and its complement will have absolutely no overlap. Think, if I die, I am not alive. There really isn't any overlap in there. I know that was a really morbid example, but it was the first thing that popped into my head. So those are two things that cannot occur simultaneously. Now, a union are things that can occur simultaneously. We can see an overlap. So event A can overlap with event B. And the union is everything that is in event A plus everything that is in event B plus that overlap in there. So let's say event A is liking vanilla ice cream. Event B is liking chocolate ice cream. Well, let's face it, you go to the ice cream shop and, the frozen yogurt place, and twist is an option. So there are those who do like both vanilla and chocolate. So the union would be those who like vanilla, those who like chocolate, and those who like both vanilla and chocolate. So that would include everything in A and B plus that overlap. So for a complement, the probability of event A plus the probability of event A's complement must add to 1. Or rearranging that, the probability of event A is equal to 1 minus the probability of event A's complement. So you know that probabilities within a sample space must add to 1. If the probability of A is, say, 80%, then the probability of event A's complement must be that remaining 20%, because that's everything that is not in event A. Now, with unions, the probability of the union of A and B is going to be equal to the probability of A plus that probability of B, because that overlap is inherently included in there. So the probability of the union would be those who like vanilla and chocolate and both. So that does include that overlap. So let's look at a union example here with our Markley oil and Collins mining. Markley probability of the union of Markley oil being profitable and or Collins mining being profitable is going to be that union symbol there. So this is going to include all of the events where Collins mining is profitable, where Markley oil is profitable, or where both of them are profitable. And we can add all of those up, so that would be 0.82%. So we're adding up all of the events within the sample space that has either a positive in the first note, a positive in the second note, or a positive in both notes. Okay, and we're going to come up with 82% there. An intersection would be just looking at that overlap. So instead of saying the people who like chocolate and vanilla, you're saying the people who only go for twist. Mutually exclusive events are events that cannot occur together. So that would be saying, kind of like an event and its complement, it's the everything else, events that share no sample points in common. So for our intersections example here, we have Markley oil is profitable and Collins mining is profitable. So these are only the overlapping positions. These are only the points where both of our observations result in a profit. And there is a 36% chance of that occurring. You can see that we're adding up those sample spaces there. The additive law says that the union of A and B would be equal to the probability of A plus the probability of B minus the intersection, because that's going to prevent any overlapping or double counting. So we knew the probability that Markley oil was profitable was 70%. We knew the probability that Collins mining was profitable was 48%, and we knew there was a 36% chance that both of them were profitable. So if we calculate the union that way, that 70% plus that 48% minus the 36% to prevent any double counting in there, we come up again with our 82% as we saw previously. Conditional probability is a little bit different. Conditional probability is the probability of an event occurring given that another event has already occurred. So we see the equation here. Probability of, we read this as the probability of event A occurring given that event B has occurred. So the one that is given is going to be in the denominator. So that would be equal to the intersection of probability A and of events A and B, so that overlap, divided by the probability of event B occurring. And then this relationship can be rewritten to show the multiplicative law. So this is just basically an algebraic manipulation. And that multiplicative law provides a way to compute the probability of the intersection of two events given that conditional probability. So we're going to look at an example here. What is the probability that Collins Mining is profitable given that M-Markley Oil was profitable? So M-Markley Oil is going to be after that line. That's going to be the given. So the probability that that M-Markley Oil is profitable is going to go down there in that denominator. So my denominator would be, given that M-Markley Oil is profitable, what's the probability that M-Markley Oil is profitable? That's going to be 70%. So you're going to see that down in my denominator. Then what is the probability that both Collins Mining and M-Markley Oil are profitable? That's at intersection there. We know that that is going to be 36%. So the probability that Collins Mining is profitable, given that I know that M-Markley Oil was profitable, is going to end up as 36% divided by 70%, or 51.54%. And we can figure out this the other way in reverse. What is the probability, applying the multiplicative law? So we wanted recalculating that intersection given the fact that we know that M-Markley Oil is profitable given that Collins Mining is profitable. So just rewriting that and showing the algebraic manipulation. This can be shown in a joint probability table. So this is kind of written in generic terms with a probability A and a probability B. So the complement of event A is anything that is not in event B. Anything that is not in event A, and the complement of event B is anything that is not in event B. So when we write this into a table, we would have the marginal probabilities would be on your right-hand side and the bottom. That would be like the probability of B occurring, the probability of A occurring, the probability of A's complement occurring, and the probability of B's complement occurring. You're probably wondering why I write that. This is the notations are the ones that are written here, and the ones where it says marginal probabilities, those would be the actual numbers in percentages. And then those joint probabilities are going to be within the actual table. Those are going to be the intersections. Those are going to be the overlaps. So the actual body of that table is going to be all of the intersections between those occurrences. So if we go back to our example here, we have probability of event M was probability that M-Markley Oil is going to be profitable. We know that that was 70%. Well, if event M is M-Markley Oil is profitable, then the complement of event M would be occurrences where M-Markley Oil is not profitable. So if the probability that M-Markley Oil was profitable was 70%, we know that our table has to add to 100%. So the probability, by definition, your joint probability table must add to 100%. So if the probability that M-Markley Oil was going to be profitable was 70%, and this must add to 1, then there must be a 30% chance that M-Markley Oil is not going to be profitable. Similarly, if we know that the probability that Collins Mining was profitable was 48%, then the complement of event C of Collins Mining being profitable must be the probability that Collins Mining is not profitable, which must be 52%. And then we can go in and look at these internal relationships here. So this 36% is the probability that both M-Markley and Collins Mining are profitable. So we knew that 36%. Well, how do we get this 34%? Well, we know this 34% then would be the probability that M-Markley Oil is profitable, but Collins Mining is not. I didn't know that number. I didn't know that intersection. How would I find it? Well, I know the probability that Markley Oil is profitable is 70%. I know the probability that Collins Mining is profitable is 36%. So the difference between there would give me the intersection where Markley is profitable but Collins is not, and that would be the 34%. So you can go in and fill in the remainder of that table using that same basic methodology. Reviewing again a little bit more jargon. Two events are independent if the probability of A occurring given that probability of B has occurred is equal to the probability of A, meaning it really didn't matter what happened, whether B happened or not, A is still going to happen. So two events are independent if one occurring doesn't have an impact on the other occurring at all. And you can go back and think about the relationships that you saw. They don't necessarily have to have any overlap, and we can rewrite this equation the same way. Probability of events A and B are independent if the probability of B happening given that A has happened is still equal to the probability of B. So it means that it didn't matter. And then remember our intersection calculations we've talked about before. This would say that the intersection of A and B is equal to the probability of A times the probability of B. So here we're looking at independent events. Let's see, are these two independent? Well, they would be independent if the intersection is equal to the probability of Markley Oil being profitable times the probability that Collins Mining is profitable. We know that that intersection is equal to 36%. We know the probability that Collins Mining being profitable is 70%. We know the probability that Markley Oil being profitable, we know the probability of Markley Oil being profitable was 70%. We know the probability of Collins Mining being profitable was 30%. So when we multiply the two of them, we get 34%, not the 36%. So these events are not, in fact, independent of one another. Okay, now we are going to switch gear a little bit and look at something called Bayes' theorem. Bayes' theorem basically says, okay, I'm going to use my knowledge of conditional probabilities, and I'm going to now add additional information. So it finds the posterior probability that event AI will occur given that event B has occurred. So we have old probabilities or prior probabilities. We're given new information. We apply Bayes' theorem and we come up with the posterior probabilities or new probabilities given that new information has been added. Now, you see a whole bunch of subscripts on here and it looks kind of confusing. Let's just go through and look at an example. But please note, Bayes' theorem is applicable when events are mutually exclusive and the union is the entire sample space. So they are mutually exclusive when the overlap is equal to 0 or that intersection is equal to 0. So a proposed shopping center would provide strong competition for downtown businesses like LS Clothiers. If the shopping center is built, the owner of LS Clothiers feels that it would be best to relocate to a new shopping center. Makes sense, too much competition, you might want to move. The shopping center cannot be built unless a zoning change is approved by the city council. The planning board must first make a recommendation for or against the zoning change. So let A1 be the town council approves the zoning change, and A2, the town council does not approve the zoning change. So there's a 70% probability that the town council does approve the zoning change and a 30% chance that the town council does not approve the zoning change. That's information that's given to you. Then let B denote the fact that the planning board makes a negative recommendation. So planning board makes a negative recommendation. And then the probability that the planning board makes a negative recommendation, given that the town council approved the zoning change, is 20%. And then the probability that the planning board gives a negative recommendation, given that the town council disapproved the change, would be 90%. And we can come up with the complements of those events as shown. So the complement of the, the 80-20 relationship and the 90-10 relationship. So we can write this out in our tree diagram as shown, the 70-30, the original 80-20, and then down there for that 90-10, and we come up with our overall expected probabilities. So that intersection then is going to be just calculated 70 times 20. It's going to give you that 14. That 7 times 0.8 there is going to give you the value as shown. Okay, so assuming that the planning board's recommendation is not to approve the zoning change, we have this information in here. Probability of event A1. Well, what was the probability of event A1? Probability of event A1 is the probability that the town council approved the zoning change. And then we had that 20% chance that the council made a negative recommendation to the planning board. Given that was a 20% chance. So we can go in and literally just plug it into this equation, and we come up with a 34% chance. So the posterior probability of the town council approving the zoning change is 34% compared to the prior probability of 70%. So that additional information definitely changes the probabilities as we are looking at them. And then we can go through and work through, a series of all of these combinations here to look at all of the potential outcomes that you would have. And this system works in the same way as we talked about before. You have to add to 100% as we move down here. So we'll go through some examples like this in a separate video where we're talking more about those applications.